This is the continuation for the previous lecture video. Here we have this equation shows the autoionization of water. This shows that water can react with itself to form ions. The equilibrium expression for this reaction is the equilibrium constant K is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. Note that these are not included because these are pure liquids, and again, pure liquids and solids are not included in the equilibrium expression. We have a special name for this constant. We call this one as Kw, or the water dissociation or the water ionization constant. And again, we have determined the value of Kw experimentally, and that's equal to 1.00 times 10 to the power of negative 14. Now let's find out the concentration of hydronium and hydroxide ion in water. To do that, let's do an ice box. That means initial, change, then equilibrium. Again, these are liquids. Liquids are not included in the equilibrium expression. Then here we have the products, the hydronium and then the hydroxide ions. At the initial or before the reaction, obviously we don't have any of the products because the products haven't been formed yet. Then we have the change in the concentration. So of course they are forming over time. So we expect the increase in concentration over time. And then for the value, let's put here x muna because we don't know their value. And then for the number here, it depends on the coefficient. So since the coefficient here is 1, then it's obviously there's no need to write 1 over here. Then if you look for OH, it has the same coefficient, so meaning the same ang change sa hydronium than the hydroxide in this reaction. Of course, the equilibrium concentration is simply the sum of the initial plus the change. So 0 plus x is equal to x, 0 plus x is equal to x. So these are the equilibrium concentration of hydronium and hydroxide in water. Of course, we need to find the value of x here. We can use this equation. So the Kw, again, it's always equal to this number, 1.00 times 10 to the power of negative 14. And then for the equilibrium concentration of hydronium, that's equal to this one, that's x. And then the same thing for the hydroxide, it's also x. And then we are finding for x, let's solve this one first, x times x, obviously x squared, then 1.00 times 10 to the power of negative 14. Finding for x, we need to square both sides. What is the square root of x squared? Obviously x. What is the square root of this number? It's equal to 1.00 times 10 to the power of negative 7. So this is the value of x here. And this one is the equilibrium concentration of hydronium and also the hydroxide ion here. Again, x is equal to 1.00 times 10 to the power of negative 7. The same thing, 1.00 times 10 to the power of negative 7. And as we know, water is a neutral substance. So for a neutral substance, the concentration of the hydronium and then the hydroxide ions are equal. That's equal to 1.00 times 10 to the power of negative 7. The same thing for the hydroxide. So for the acidity and then the basicity, we of course it can be based or on the hydronium or it can be based on the hydroxide, but we commonly base it using the hydronium ion, and that's equal to 1.00 times 10 to the power of negative 7. This is for a neutral substance. So again, when the hydrogen or the hydronium, it's the same thing lang, di ba? That's equal to, if that's equal to 1.0 times 10 to the power of negative 7, that is neutral. And then if it's less than this one, it's acidic. And then if it's greater than this value, that one is basic. Let's emphasize this one by analyzing this. Again, for a pure water, it's neutral. So its hydrogen ion concentration is 1.0 times 10 to the power of negative 7 molar. If we expand this number, because it's a scientific notation and it's not very common for everyone, let's try to expand this one is equal to 0.000001 molar. Again, this is for a neutral substance. Let's take a sample strong acid. So let's say a strong acid has a hydrogen concentration of 1.0 times 10 to the power of negative 2. And if we expand this one is equal to 0.01 molar. So as you observe here, pagka strong acid, it has a larger amount of, again, this one is the hydrogen ion or the hydronium ion concentration. So as you observe here, this number is bigger than this one because again, this number is less than 1. So obviously pag mas less ang 0, it is smaller compared to this one. So we can see here that for that strong acids or acids, they have a higher concentration of hydrogen or hydronium ions. It's not very um, obvious first because we thought that this one might have a higher concentration, but again, this one is a negative exponent. So pagka mas malaki yung negative exponent, mas maliit yung value compared to this one. So again, acids, they have a higher concentration of hydrogen or the hydronium concentration. How about for a base? So for a base, the hydrogen or the hydronium concentration is equal to 1.0 times 10 to the power of negative 12. So it has a big exponent. Pero again, since this is a negative exponent, we expect this one has a lesser amount. It's actually very, very small compared to the concentration in neutral and also in acidic solution. Again, this one is basic or base. This one is an acid. So, of course, when we try to describe the acidity or the basicity of a substance, it's awkward to say these things, or it's not very convenient to tell that its hydrogen concentration is this number or this number or these numbers. So, we need to find a convenient scale on describing quantitatively the acidity or the basicity of a substance. And with that, we can use the logarithm. Of course, we can use the logarithm um, to uh, to show or to represent very small or very large numbers. So here, a logarithm is the power or the exponent to which a number must be raised in order to get some other number. And with this, we use the pH scale for this one. The pH scale is simply equal to the negative log of the concentration of H plus, or it can also be equal to the hydronium. Again, this is basically the same thing. Again, pH is equal to the negative log of the hydronium ion concentration. Okay, let's determine the pH of this pure water here. Again, the pH is equal to negative log of the concentration of hydrogen ion. Then to solve this one, it's negative log. And here our concentration of hydrogen ion is 1.0, 1.0 times 10 to the power of negative 7. Let me just check. Okay, good. Okay, so if we use our calculator, so let's use this one here. Negative log. Okay, first let's input our value here. That's 1.0 times 10 to the power of negative 7. Then let's get the log of this. That's equal to negative 7. But here we are asking for the negative log. So what's the negative of negative 7? That's equal to 7. So the pH of pure water is 7. So again, this pH is simply it's simply the negative log of this concentration of H plus. So we just simplified, instead na this number, we converted it to a log na mas easier ang pag-determine or ang pag-describe. Then here for a strong acid, Again, pH is equal to the negative log of the concentration of H plus here. The concentration of H plus here is uh, 1.0 times 10 to the power of negative 2. So it's base 10, so I think it's very obvious. The log of this one is negative 2, and then what's the negative of negative 2? It's equal to positive 2. So the pH for this one is positive 2. So how about for this base over here? So for this base, again, the pH is equal to the negative log of the H plus. That's 1.0 times 10 to the power of negative 12. And it's base 10 over here, so we can easily determine this one as equal to 12. So the pH for this strong base here is 12. Okay, so as you observe here, so pagka mas malaki yung concentration ng hydronium, mas maliit yung pH. That's because again, our pH is a negative log. So everything is reverse here. So again, pag mataas yung concentration ng hydrogen or ng hydronium ion, mas maliit yung pH because again, the pH is the negative log. So it's simply the opposite. So if we compare this one, acids, they have the smallest pH, and then a small pH means um, it has a higher number of the concentration of the hydrogen or the hydronium ion. So again, for pure water, that's 7. Then for base, that's 12. Of course, for the pH scale, neutral, of course, that's 7, right? That's the neutral. Then if it's less than 7, acidic. Then if it's above 7, that is base. Of course, it's commonly from 0 to 14. Ang center is 7, and again, that is neutral.